So the next speaker is Viktor Kuncak. So Viktor is a professor at DTFL. He's done many contributions to constraint solving and decision procedures. Recently, he's been working on this very interesting work, which is essentially applying constraint solving and decision procedures at static time, but at runtime. And so he'll touch about this today.
Thank you, Martin. And I apologize for coming only today. This is still a little bit earlier than Martin Večev's visit to EPFL, about which he can tell you more about on another occasion. I will tell you about executing specifications using the dynamic approach, as Martin mentioned, and also trying to compile it in as many cases as possible. And I also spent some time trying to motivate why we would like to execute specifications, although in some sense it boils down to the saying your wish is my command. So let's start with a very simple wish, which is sorting a list of numbers. We are given a list of numbers, and we would like to make it sorted. So let's suppose that this is our wish, written in English. It has two parts. The part in the black talks about this list. So somehow the result should be the same list, in some way, same. And it should also be sorted in addition. Okay. So this is a statement in English. And these two parts you could describe graphically. For example, that the same list means that the output list is the same multiset of elements, or perhaps weaker, same set of elements as the input list. And sorted, of course, means that in the resulting list, elements are in order. Let's assume in ascending order here. Corresponding to this wish, we would like to formalize it, and our decision will be to formalize it using executable predicates. So these are predicates that take the input and the output of the program that we would like to construct or to execute, and then state what does it mean for the input-output relationship to hold. So in this case, I'm writing that the content of the input should be equal to the content of the output, and content here will be computing a set. And isSorted is a recursive function that takes a list and then checks whether it's sorted. Okay, so the specification checks for a given input and given output whether that output is acceptable. And if you look at an implementation would be, for example, some sorting algorithm. It would be a function from a list to list. And this function should be a subset of the relation that's specified using that predicate. So we have, as expected, fewer behaviors for the function. And we'll be looking at total functions in the end. We would like to construct total functions that are subset of given relations. Okay, so now there is a gap between the ways in which we would formally write the specification and the implementation. One is just these functions that I stated above, and the other one would be some particular sorting algorithm. And what we're interested in is somehow bridging this gap between the specifications and implementation, both of which are these formal artifacts. Okay, so in the grand scheme of things, wishes are perhaps somewhat informal, and there are different ways in which we could try to flesh them out to make them more precise. Specifications of the kind that I'm talking about here are one particular kind for the case of, let's say, functional programs. And so we are looking at bridging this gap. And then once we obtain implementation, then of course we can bridge the gap further to machine language and so on using compilation technology. So there's several approaches that one could look at, and this covers a number of different techniques. Checking assertion at runtime is perhaps the simplest thing that you could do. Verifying that the specification holds for all possible inputs would be a somewhat more ambitious goal. And in both of these cases, you have both the specification and the program, so you're just checking consistency. And in the other two approaches, you only have the specification. You are trying to use the specification in some sense as a program. So in constraint programming, for every particular I, you will be finding the output that satisfies the specification. So the constraint solving happens in runtime. Whereas in synthesis, we would like to construct this function. In this case, again, it's a particular form of synthesis from inputs to outputs. So it's not a more general reactive synthesis. So this happens to compile time, and there are essentially these two axes, whether I have the program or not, and whether things happen at runtime or compile time. And you can view, of course, that compile time is to some extent optimizing the runtime, but also providing us more guarantees. Okay, so I apologize. Let me just look quickly at checking assertions to introduce the language that we are using. So this is an actual piece of code that checks whether a given sorting algorithm satisfies the specification. I already wrote this specification before. Using in Scala, we write specifications using post conditions here, using an ensuring clause, and this always just a bound variable that is always bound to the result of the function. So always the output here. And this arrow is a part of lambda abstraction. So it's a function from output into the condition between input and output, where input is visible as an argument of the function. And now these functions that appear in specifications themselves, they're actually executable functions themselves. And we will assume that they're terminating executable functions. We have some techniques to check termination, but I will not go into them in this talk. So we have some specifications that are predicates. And then when we run this, then the compiler will simply execute them at the end of the procedure. And this will work using the standard programming language. So here, this is all Scala, and using already existing constructs in Scala, you can do runtime checking. Okay, so this works by construction without any special techniques, because we have chosen that our constraints are programs. If constraints, for example, had some quantified predicates or were otherwise more expressive, then we would not be able to do it that way. Now, so how do we give some stronger guarantees? That leads me to the next question, verifying that the program always meets the specification. So now the input is again the same, and I wanted to emphasize that because I think if you write the system so that runtime checking is the same as takes the same input as verification, that makes it more accessible to programmers. So in this case, we would like to be able to write something like this and then check whether for every input the post condition will be satisfied, or get a counterexample. Of course, in some cases, we'll get a timeout. Okay, so we have the tool that does this verification. It's called Leon. You can find it here on this URL. And basically, as you type it, it's compiling the program. It's generating verification conditions. It's checking them, and it's displaying here results. Here's a result of insertion into a sorted list that you can see here. With this specification that's somewhat stronger than what I said here. And you can see here that all the functions verified. Now, if you take a buggy version, here I have changed the body so that there's an error here. You can see, so this was insertion into a sorted list, but normally insertion should actually check where you should insert. This one doesn't, so it always ends up being inserting at the end of the list. And therefore, this predicate here is sorted, will be broken. And if you if you click on that icon over there, you will see that you get a concrete counterexample that tells you for which input list and which argument you should run it so that the post condition does not hold. And this happens, you can see these are fractions of seconds for these kinds of programs. And checking is to a large extent done modularly, although in the limit, if the specification of a function is not given, then the body itself is used instead. Okay, so we have verified a number of small, but I would say interesting data structures and other programs that manipulate algebraic data types and lists and so on. And this is work with Regis Blanc, Etienne Knois, and Philippe Suter, who started this work and who is now at IBM Research. So you can see that verification times are reasonable. And I would like to say a little bit about the kinds of techniques that we are using in here. So one of the main techniques is to take these recursive functions that have post conditions, and let's focus on this post condition here for sorted ins function that we have seen. The post condition says that the result, the set of elements in the result is the original set of elements extended with a given element. And we invoke the function recursively, so the standard thing to do is to replace the recursive call with the specification itself. If you do that, then you get a simpler formula in that it no longer talks about sorted insertion. So this function does not appear. We have generated verification condition specifically for it. On the other hand, we still have other recursive functions, namely recursive functions that we have used in the post condition in order to specify what does it mean to have to compute a set of elements inside a given list. So even though certain recursive functions have gone away, some other ones have still remained. So we need, in some sense, technique for proving, for solving constraints that involve recursive functions. So now, of course, if we added arbitrary computable functions over this countable domain, we would get a Turing-complete formalism. So we are interested in some simpler functions for which we can still get tractable decision procedures or verification condition generator solvers. So the kind of functions that we have looked at generalize this notion of content of a data structure. So content can be actually written as a threefold, which means that you have defined operation for the leaf of the tree, you define a constant for the leaf of the tree, an operation to do in the middle of the tree, and then this gives you the expression to evaluate for a given tree. So if you compute the size of a tree, you put 0 in the leaves, and you put +1 in the middle in each node, and so you're summing up recursively left and right tree. So you have this function that takes 2 arguments and computes first argument plus second argument plus 1, and this will compute the size of the tree. And similarly for content, the set of elements, you will take empty set in the leaves and then take the union with the element that's stored inside the tree. So these kinds of functions are catamorphisms over the corresponding algebraic data type or threefold. So they cover actually a large number of useful functions. But in order to obtain a constraint solving procedure, so something for which we can still check whether the formula, such as the one that I've shown, holds or not, we impose some additional restrictions here. And the additional restriction here is satisfied for functions like size and content. And it means that, so the particular restriction says that if you have multiple trees that map to the same to the same value, then this is acceptable. But if you had, for example, injective function, this would not be acceptable. So we call this condition sufficient surjectivity. And it basically means that if you take the inverse image of an element in the result, then you will get a large number of elements. Okay, so there are many different trees that have the same size, and there are many different trees that have the same set of elements. So for those kinds of trees, then we have a constraint solving procedure that I'll elaborate a little bit, and that actually turns out to be a decision procedure. So the idea is very simple. If you have recursive functions, one of the main things that you do is unfold them. So let's say we want to prove something about size function, that size is less than 1, as an example formula. Then you would initially just treat it as uninterpreted. Then you would add 1 level of definition and 2 levels of definition and so on. Okay, and you essentially repeat that and make it do both over and under approximation of the constraint. Each of these attempts is given to an underlying solver that understands uninterpreted functions that are simply functions that from first order logic, about which we know nothing other than for same value we get the same result. And they also understand arithmetic inequality. And so if we unfold the function some finite number of times and then leave the innermost unfolding unspecified, we will get an over approximation of the behavior, because we are simply not saying what the innermost recursive function call does. In this way, if we obtain unsatisfiability, suppose that we are lucky and we obtain unsatisfiability of the constraint, then we know that the original constraint was also unsatisfiable. On the other hand, we would also like to check for under approximation so that we can report valid counterexamples. And in this case, we simply convert this formula so that the innermost recursive function call is not used. So you don't make use of that. And this is not perhaps a bit less obvious how to do it in this functional form with if then else terms. But if you transform it into actual formulas by appropriate flattening, then you can simply block, in a way, remove the appropriate disjuncts. And we do this removal using by introducing propositional variables and using efficient interfaces in SMT solvers to do that. So as a result, we get a series of over and under approximations of these recursive functions. And what is interesting is that for this class of theorems that contain, for these kinds of functions that contain functions that compute set of elements of a tree, or the size of a tree when you know that the size is non-negative, and several others, you actually obtain a decision procedure. So this process terminates. So why do you obtain a decision procedure? Well, one direction is actually obvious and more general, which is that if you get a satisfying assignment while ignoring the uninterpreted parts, then this is sound. And the other part is also clear why the result is correct, but why would you obtain termination? That requires a little bit more analysis. But it boils down, of course, to this condition that we require here. If you have sufficiently many elements, then a counterexample for uninterpreted functions can be mapped to a real counterexample for actual recursive functions. Okay, so compared to, let's say, small model theorems that are very useful for a number of logics, here for unbounded domains, we try to, either when we use quantifiers, to use some sort of finite quantifier instantiation theorems, such as local theory extensions that have been studied, among others, by Viorica, Sofroni, Stockermans. And in this case, we have a form of quantifier instantiation which corresponds to the definition of recursive function. Now, this is not a substitute for domain-specific reasoning, and this is extremely useful technique, but I would like to mention that in some other cases you do need to go into further details. So, for example, if you want to think about multisets instead of sets, so my specification previously used sets, then if you also allow cardinality constraint on multisets, then you basically have an very interesting class of constraints that you can still show to be decidable and in NP, but whose implementation is challenging. And there we have some prototype, but integration into, let's say, SMT solvers, full-fledged SMT solvers, is still to be done. So this technique is based on reductions to the basically integer linear arithmetic, but through things like semilinear set representations of the Pressburg arithmetic formulas. Okay, so I just gave you an overview and highlighted some of the techniques that we use in order to verify that program meets the specification. And that's one way to somehow relate the specification and implementation. And now I would like to move towards having only the constraint and trying to somehow treat them as programs. And it turns out that this will be related to the technique that we use here, because we need to, again, find some value. And what kind of values were we finding in the case of verification? Well, we were finding counterexamples. Right? So we would like to use the technique that was used to find counterexamples for specifications, in this time to find the values that satisfy the specifications. So in some sense, you would like to use assertions to compute. And in runtime checking, an obvious question is what to do when an assertion fails. So it's common to crash the program, but in some cases, this may not be the ideal outcome. So some people are looking, for example, at data structure repair. Or in databases, you could specify user-defined triggers, for example, for certain integrity constraints. But you could also say that, well, if some part of the program is wrong and we could somehow anticipate it, then you should state the properties that you would like and not say how to compute some of the values. And this leads us to constraint programming. So in constraint programming, we are not stating just constraints on the known values, but also constraints that involve some values that should be computed. Okay, so this is what is already done, for example, in constraint logic programming. But in our context, we have a richer class of constraints, and we are using, let's say, somewhat different platforms and different interpretations of the underlying programming language semantics. So essentially what we do is we take the constraint solving techniques based on recursive functions and the underlying SMT solver. In our case, we use Z3. So we take it and we allow to embed in the program the constraints between inputs and the unknown outputs. And then we can just write the specifications. So here are some results when you, for example, specify additions into lists or removal into lists, as well as addition and removal into trees. So you can see that up to a small number of nodes, these are still around 1 second, and then the process is exponential, especially for more complicated data structures. So the execution time becomes slow because every time you're invoking this decision procedure that is typically for an NP-hard problem. Nonetheless, the technique seems very appealing for prototyping because the only thing that you would need to write is what we had before for specification. So you describe the content and it's sorted, and then if you want to sort a given list of elements, you write the set of elements that you would like to get and say, find me a list that is sorted and whose content is equal to these elements. And it computes what you would like. Okay, so here's another example that actually has to do with termination, but in our case, termination is enforced by construction. So this comes from a code that was used inside a music player in a boot sequence. So it's a C code that is just supposed to convert the total number of days into the current year since 1980 and the leftover number of days within the year. So the computation was done in this way. So it's roughly dividing by 365 and taking the remainder, but the remainder, sorry, and you still need to take into account leap years. Right? So suppose that we have some function whether a year is leap, and this function can be actually written down using some linear constraint. And so this was the code that was written. Unfortunately, on December 31st, 2008, which is when the problem was discovered, the music players that were running this froze in the boot sequence because this was running in the boot sequence. And so can someone see why this is the case? So you can take the hint from the 31st of December, 2008. 2008 is a leap year, and 31st of December. No, actually, there's no minus in that case. So if is leap year, you are entering this if statement, right. But the days is not greater than 366 is equal, so you do nothing. So this is a very efficient infinite loop, so you're really not doing anything. And so this is a termination that I think we would find even perhaps a counterexample for termination using other techniques. On the other hand, what I would like to suggest is that if the program is as simple as that one, you can actually describe it. Here's a function that says what it means, that computes the number of leap years until some value. So this is using the computation that takes into account every fourth year is leap, unless it's divisible by 100, then it isn't, unless it's divisible by 400, then it is. So that's also the definition that was used. But still, it's a somewhat complicated expression, perhaps, but it's a linear arithmetic expression, integer linear arithmetic. And then what I would like to do is solve this constraint. So knowing the total number of days, and this is this variable here, days, I would like to find the unknown year and day. And so the total number of days should be possible to compute back the total number of days by taking year minus origin times 365 and then adding the leap days, right? So days accumulated through leap years, and then the current day within the year. So in some sense, in this case, it seems clear that specifying the inverse of the function is easier than specifying the function itself, and that's what we are doing here. The constraint is also, of course, that day is within 0 and 366. And Of course, we could have still made a error in the specification, and perhaps we did, but the point is that no matter what we generate, it would satisfy the given constraint, so we could then further analyze it at the constraint level as opposed to analyzing some program with loops. And in any case, if you use our techniques, actually you have ensured termination. So either you use a decision procedure to solve this, or as we will see later on, you can actually convert this into a program that has only constant bounds on loops. Okay. So let me give you another example, and this is perhaps still towards motivating why we like to execute specifications even if it's very inefficient. This is the very widely used textbook on algorithms that describes red-black trees. So red-black trees are described as search trees that satisfy a certain invariant. So search trees means that the nodes are in order, and the further invariants talk about the relationship between alternation between red and black nodes inside that ensure balancing. But so the key invariants are actually specified in really only a couple of bullets of English, but still it's fairly short. Now, the implementation of red-black trees is the next 30 pages with explanations why it works and so on. So we can see that still natural language specifications appear both more natural to present first and also more concise than actual implementations. And so the hope is that the formal specifications are one step closer to these kinds of descriptions as well. Because indeed we go invariant by invariant and we write down functions that, for example, check whether something is balanced, whether the nodes are sorted, and then we conjoin these different properties to define that something is a red-black tree. So we have a function that given a tree checks whether it's a sorted red-black tree. And then we compute this content function that takes a list of elements stored inside a tree. It computes not a list, a set. It computes a set of elements stored in the tree. And then finally, once we have done all this hard work in formalizing specifications, we can write down insertion in just one line. So we say choose a tree which satisfies the invariant and whose content is content of the original tree plus the new node to be inserted. So we get a huge savings. Now you might say, well, but you had to specify all these functions, content and is red-black tree invariant. On the other hand, this is still not actually more effort than writing implementations. And it's more importantly, it's the right kind of thing. We should be spending time thinking about that. And I would also like to emphasize that this promotes reuse. Because suppose that now, after having insertion, you would like to implement remove operation. If you were writing this in conventional style, you would have to write at least 140 lines of some C code. So this is removal from red-black tree. Whereas here you would just, once you have all that in place, you would need to replace this minus with this plus with minus. That is true, but even in Scala it would be longer than one line. This will not remove in log n time. That's exactly the problem. That's why we have not quite yet revolutionized the thing, but we are working on we are not quite there in terms of the performance. As I mentioned, this is if you execute it at runtime, you will get exponential time solving process, right? Mm-hmm. Yeah, you're absolutely right. So the specification is also under constraining the result. Yes. On the other hand, the semantics that we have is that you can choose whichever one you would like. So you are free to choose the one that is easy to compute in log n time. Right. So if we have a very smart way of executing this, then we would be able to do that. And that's sort of what the challenge for the future is. So in terms of expressive power, we can also compute the constraints at runtime, although in many examples we actually have statically embedded constraints as well. And another useful thing is to enumerate multiple values that satisfy the constraints, because that has applications in automated testing, and we have compared it and got results that are in some cases close to Corrad tool for test generation that was tailored for that task. And as you mentioned very correctly, performance is the critical thing, right? So in order to obtain something that is more predictable and it has a better performance, we are working on synthesis techniques. So synthesis techniques will try to compile this process of finding the value for a given input. You would now like to say what is the most efficient way to do it. Well, you would like to ideally come up with the best algorithm that can satisfy this specification. So I'll give you some examples for when this works. So one class of examples are specifications in integer linear arithmetic. Again, that's similar to the example with the music player. So we're decomposing number of seconds into some hours and minutes. And so the code that comes out of our tool is something like this, where we are performing the divisions and modulo operations. So you get the total number of seconds in a way that is very similar to what you would probably write by hand. And again, I would argue that writing the inverse of the function is easy. And even though the code is actually not shorter in this case, some of these constraints on the hours and minutes actually should perhaps be inferred from a sufficiently rich notion of types. You have some types that constrain the values. And then, as I mentioned before, if you have immediate ability to analyze things without first converting it through some verification condition generation process, if you underspecify the computation, then you can get counterexamples for essentially determinism. Right? So specification has multiple possible values for the same input. So for the total number of seconds of 60, if you weaken the specification to allow minutes to be less than equal to 60, you would get two different solutions. And there's also you could get warning for the cases where the function is not total. So in other cases, you can then reduce the problems to, for example, integer linear arithmetic. So this is an example of a theory of sets with cardinality bounds. Which is somewhat easier than multisets with cardinality bounds, and we have also the procedure to solve such constraints. This particular example takes a set of elements and tries to split it into two elements. This is what this line says. Right? Union is equal to a given set, and intersection is empty. And the first two lines are saying that it should be balanced partition. So one thing says that it's partitioned, the other one says that it's balanced. And of course, being able to conjoin these two orthogonal concepts seem useful. And so you get as a result a simple splitting function in this case. Okay, so what is the idea of doing these kinds of compilation steps, transforming relations into functions for, let's say, decidable theories? So you can think of it as doing Gaussian elimination, but for certain classes of programs. And certain classes of programs do correspond to certain kinds of equations. So for integer equations, you could use Euclid's extended Euclid's algorithm that computes the characterization of the set of solutions. And this is something that we make use of, but also you would like to support disjunctions, negations inside these specifications. And this can be also done. So we have shown that you can do that. And in the end, you can have a procedure that takes arbitrary specifications between inputs and outputs when the specification is written in Pressburger arithmetic. And it then always terminates. It produces the code that always satisfies the specification in the sense that it computes the result that satisfies given input-output specification whenever one such output exists. Okay? And what about the cases when no such output exists? Well, it's going to also produce the precondition, so the formula characterizing the cases when the output exists. Okay? So this is what you can do for some very nicely behaving theories, such as Pressburger arithmetic. And we would like to do that for more theories, in particular for as many building blocks that are used in constraint solvers as possible. So just a summary. So what is now the comparison between decision procedures, which are used to answer these constraint solving problems and to do verification, and what we call synthesis procedures. So in decision procedure, you get some constraint, and then you give a constraint to the procedure, and well, the term decision procedure really should say that you say yes or no, whether it's, let's say, satisfiable, if it's decision procedure for satisfiability. But in practice for verification, it is common to refer to some additional functionality. In particular, model generating functionality is extremely useful to get concrete counterexamples. So you would like to take a constraint, and then as an output, you get the values for variables that satisfy the constraint, like one example solution of this linear integer equation. In the case of synthesis procedure, we have two classes of variables. We have parameters, and we have the outputs, what we call outputs. Now, outputs have similar status as the variables here. Whereas the inputs are, or parameters, they are fixed, and you're supposed to express the outputs as a generic function in terms of inputs. Okay, so it's output is a program that computes the outputs given the inputs. And you can also think of it as parametric decision procedure. So in terms of the framework that we use in order to describe these different steps, it's similar to frameworks for describing, let's say, decision procedures. So these brackets here are just sort of syntactic notation. What we have is some synthesis predicate. This is this constraint, so this is a formula. And we indicate explicitly the input variables and output variables. And the main relationship here, and again, I apologize if you expect different meaning from this symbol, but this just means that we can transform this problem into the second problem, okay? So it's just a symbol, and the meaning of this symbol we define as follows. So it needs to be refinement, which is domain preserving. Refinement just means that the resulting constraint is stronger than the original one. It denotes a smaller relation. And domain preservation means that we don't lose existence of total functions as a solution. So if there exists a solution for the first constraint, then there exists a solution for the second constraint, and that needs to hold for every variable. So the parenthesis is here for every input parameter. Okay, so these are the kinds of relationships that we would like to establish, and then compose them together to get procedures that will do synthesis. There is a special case of our result. These are relations that are actually programs that say the output is equal to a given term that contains parameters, and there is a precondition, so some condition that should hold. So you can think of that as just a shorthand for this. And then the refinement becomes just the fact that when the precondition holds, then the constraint needs to hold for for the values computed by the synthesized program. And also the domain preservation reduces to this condition. So if basically reduces to this implication with the precondition, but together with the other one, then you get that P is in fact exact precondition. And that we can, so P would compute precisely when the outputs can be found, and T would give a uniform expression that gives correct results whenever precondition holds. And really, this generalizes quantifier elimination. You could even go so far to say this is quantifier elimination, but a very particular constructive version of it. Because this problem, where you're given some parameters and you are trying to construct outputs denoted by X, corresponds to or subsumes the quantifier elimination problem. Does there exist an X? And this result, in fact, the precondition that you compute at the end is the result of quantifier elimination, whereas the program that you compute, so this precondition, whereas the program that you compute are witness terms for these quantifiers. Okay. And so because we allow, for example, conditional terms inside our language, then we can have witness terms in more cases than some simple languages for Pressburger arithmetic would have witness terms. So these conditional terms are, of course, useful, and they're useful in programming as well. And they're also common in SMT solvers. So we also allow them, which makes it possible, for example, to give such definition for K-split. So these rules. Rule for k-split, you would read similarly as in some deduction rules. It describes, in this case, what happens when you have specification which is a disjunction. So in order to come up with a program for disjunction, we will first try to come up with a program for one case and then program for the other case. Each of them will come up with, will result in some precondition, P1 and P2 respectively. Then the result will be the disjunction of these two preconditions. And here's the program. This is one of the possible programs, of course. It says that if first precondition holds, then I'll just take the first result. Otherwise, I'll fall back on the second result. And because I have this condition, then in the second case, I know that P2 will be satisfied. And of course, one-point rule is one of the most widely applicable rules in quantifier elimination. And for that rule, the synthesized program is just a let expression. So if you know what the result should be equal to, then of course you put that into the program, and this rule just formalizes this. And there are many other things that are specific to theories, and often they can be just done by transforming the specification itself. Just like in quantifier elimination, you can often transform almost all steps into one-point rule and k-split. For example, for Pressburger arithmetic, what remains is then theory-specific transformations that can be expressed simply by saying the two formulas are equivalent, so for all parameters and outputs, and therefore you can use one instead of the other for synthesis purpose. Okay, so this is how it looks like. Now, I could give you an example, let's say for integer linear arithmetic, just to see that we have also inequalities, and they are perhaps a bit more. So if you know solving Diophantine systems of equations, then you know how to handle equalities. For inequalities, again, you know that if you know how to do quantifier elimination for Pressburger arithmetic. So here's how it looks like in this example. So given A, we are trying to come up with X and Y that satisfy these constraints. What we will do is find the set of all solutions of this equation for an arbitrary parameter A. And this is a one-dimensional space that is determined by parameter T, and X and Y are equal to this. So extended Euclid's algorithm gives you this. You can try to plug it back in, and you can see that -7t and 5t will cancel, and these two will satisfy the constraint. So now, once we know that, we have a substitution that we can then plug back in once we get the solution for t. So this is what that rule formalizes. It says that t will be equal to something that we'll compute, and then we'll compute x and y in this way. And then we substitute back the definition of x and y into the constraint, and we get the other constraint over there. So it reduces to 7t less than equal to a, and 5a less than equal to 12t. And this is now a set of constraints that have lower and upper bounds, and we can take, for example, in this case, we take one of the bounds, so lower bound. So the result is this one. So 5a over 12, it's a term that contains input, and we get a precondition that lower bound needs to be less than upper bound, and we can use this then term to compute it, and this is our synthesized program. Okay, so I have shown you how you apply these rules backwards, basically, in this one example. So now we have done this for some decidable theories, including integer linear arithmetic, and theory of algebraic data types that also has quantifier elimination. So we were able to use similar techniques. But in order to get even something like sorting, you actually need to synthesize recursive functions. So this does currently work in this system. The same system that I was using to show demonstrating to show verification. If you go there, you will see also synthesis benchmarks, and you can try it out. And so Etienne is here, yes, in the third row, and he can also give you some more demos. So the idea would be then we would also like to synthesize the recursive functions. That's what the system can currently do. But for that, it's not enough to just use rules that are complete. Just like for theorem-proving tasks, you want to use techniques that sometimes leave the space of ahead of time decidable problems. So problems that you know ahead of time that are decidable. And so here we therefore use proof rules that generate this large search tree, and we expand it. And if we manage to close all the branches, then we have a synthesized program. In order to generate recursive functions, we have certain built-in recursive schemas. And in order to quickly generate certain expressions, we have techniques to also enumerate expressions. We have been somewhat reluctant to do expression enumeration, but in the end, the generate and test approach turned out to have some benefits as well, because it's not so easy to do local search and know what is your next step. And so we do a simple cost-based search over this tree. And there are some other techniques that you can read about in our UPSLA paper. In particular, we do use counterexample guided inductive synthesis, which means that when you are trying to synthesize a program, you have a candidate, you find out a set of counterexamples if the candidate does not satisfy the specification, and then it's much faster for the next candidates to use these example inputs to quickly rule out the future wrong solutions. And in some cases, we also use the candidates that are somewhat promising in order to derive conditional, basically to derive if-then-else statements that solve the problem in one case. Okay, so this is the and/or search tree that I mentioned. So it's a search tree of these different rule applications that we use. And so if we close it, then we are done. And I mentioned generation of expression terms, for which we actually have two different techniques. One of them uses SMT solvers in some sense to enumerate programs, and the other one uses type-based enumeration. This is the INSYNT work, and I think Eran will talk about the related techniques as well. And here we basically find the set of terms of a given type with some possibility to bias this set. Okay, so this gives you an overview of what we are currently doing in synthesis in this particular system. There are other things that where we use transformation-driven synthesis. This is in a different project with Christoph Koch, where we were deriving external sorting algorithms using equivalence-preserving transformations. This is what is implemented in the Leon system. Now, these two techniques that I described, constraint programming and synthesis, are still rather complementary, because constraint programming applies much more broadly, where synthesis is more predictable when it succeeds, and it often generates better code. So we have a way to combine these two, and this is what we are planning to explore further in the future. So the idea is that this search tree you can, in some sense, close any time by inserting calls to the constraint solver for all the synthesis subproblems that you did not solve yet. And these will be hopefully simpler problems, so you will be able to have better performance on the smaller subproblems, whereas certain branches will be synthesized, and then you will be able to actually execute them more efficiently. So here's one simple example that shows how this can be useful. So this example works, and is one of the last things I will mention here. So it's the case where we are synthesizing a data structure with a cache, and we would like to come up with a member data structure that is checking whether a given element is inside the data structure. So the proof rules that we have will generate a case split in order to generate code that checks whether the given value is already in the cache. And that code can be synthesized, as well as the code for the case of data structure being empty. And then there's of course the leftover, the hardest part, that we leave to the runtime constraint solver. On the other hand, we did sort of the cache does serve its purpose in that the fast path is executed efficiently. So in that sense, even a relatively moderate success of synthesis can at runtime give significant improvements to a runtime constraint solving approach. So I have some other points that I would like to mention, but that's basically what I wanted to bring to your attention. So just the different techniques that we've been using in order to use specifications as a way as something that you should focus on. So we are really working with rich specifications in this functional domain as a way of writing programs and still trying to get reasonable outputs. Okay.
Any questions?
First program, you make combos, you do quantifier elimination.
Yes.
How do you deal with the combos?
Using variable substitutions. So that's why I mentioned Euclid's algorithm. There are different quantifier elimination procedures, and each quantifier elimination procedure will give you a different. So basically, it'll give you a different synthesis procedure. And in the precondition itself, we do need to have divisibility predicates. But basically, here, if you have that something is divisible, let's see, the canonical.
I mean, suppose you have just a bunch, you end up with a bunch of inequalities and divisibility.
Yes, right. So the rule for divisibility, in this case, we didn't have it just because it was A. No, I mean, we use these fractional conditions. So in the end, it's the bad case of quantifier elimination, which is that you get big disjunctions, also happens here. It's just the way we express it is slightly different. We first go to the lower and upper bounds with these divisions, and then we look at what the remainder is. And so then in the worst case, we iterate over the possible remainder. So that's sort of the.
But do you get closed form solution, or you get alleviated loop, because you need to find the.
For Pressburg arithmetic constraints, you do get closed form solution, but it is it's a loop with bounded constant. So we do generate a loop because that's the right thing to do when you're generating programs. But in terms of quantifier elimination, you would write it as a big disjunction. So the terms are terms that do check. So it's just an expansion of this case-split rule, a very bad and big case of case-split rule, and that's the worst case. That whether it arises or not depends a little bit also on the order in which you eliminate variables. So in that sense, even though I said that it works for Pressburg arithmetic, in terms of efficiency, there's still interesting questions to be explored. In practice, how do you generate the most efficient program that, or even the smallest program? So even syntactic conditions would be interesting to combine with the fact. So once you know that it's always possible to generate a program, and you know that the equivalence of programs is decidable, there are a lot of things that you could try to do in terms of quality of generated synthesis code.
I would like to come back to the verification part of the presentation and program theory. So if I understood correctly, your language allows you to define something like primitive recursive tree functions, right? So you have certain base cases for the trees, and then use certain combination operators, let's say in the inner node, right?
Yes.
Okay, so if you were to give those proofs by hand, you would use something like primitive or inductive reasoning, right? You would show that this program is correct for the leaf cases and then use some kind of induction for handling the inner nodes. So how does this relate to your unrolling where you have, so this is a kind of bottom-up proof technique, whereas your unrolling is more top-down approach, I would say. Can you say how these two relate? Couldn't you use this inductive idea for giving complete proofs, or at least for restricted cases? Or?
Well, our system does allow you to write whatever postconditions you would like. So if you know what the inductive hypothesis is, then you can make it. You can write it down. So if you strengthen, sometimes you would like to manually strengthen these specifications. But if the specifications as written are not inductive, then what the system will end up doing is a form of K induction. So you can think of it like that, because the fact that at some level of unfolding there's nothing more to do, the problem becomes unsatisfiable in case of valid conditions, means that some k inductions succeeded for the specifications that you wrote. So that's one way of thinking about it. But the point is, see, the question is where these specifications are written, because functions like this, they really define what you want to talk about. They're defining content. So there's no, well, what would you specify them with? They are the ones that actually define your operations.
So I have a quick question. So this question of complexity and all these things, right, it kind of comes from not having the ability to guide the search and
complexity in runtime constraint solving?
No, complexity like getting the result, like your n log n or whatever algorithm, right? So what people have done for these things is like all this partial program business, right? You have the template and you leave some things blank. And so you kind of sketch how the complexity, what the complexity is going to be, but you leave a lot of things blank and figure this out either with constraints or with some other way. Can you combine this with, if I have this approach to like partial program to synthesize the whole?
Yes, so we do allow these choose constructs with unknown functions to be placed inside arbitrary contexts, and you do allow, we can have multiple choose constructs. It's just that our constraint solving, our synthesis techniques are currently very local, so they will expect the specification to completely characterize what you need in that choose construct. Although some of the techniques that we use are more general than that, and they could indeed be applied to programs with holes, so to templates, partial programs. We just haven't applied it because of the way the system is currently constructed, so it's a matter of evaluation. It's definitely a useful way of constraining the desired behavior.
Okay, so the lunch is here, so let's thank Viktor again.